Have you ever felt a profound, inexplicable sense of déjà vu? A fleeting moment where the present seems to echo a past that never truly happened? Or perhaps, in the periphery of your vision, a shadow flickers, a movement so swift and insubstantial that your rational mind dismisses it as a trick of the light? What if these moments are not tricks? What if they are something more? Glimpses through a crack in the fabric of reality? Faint whispers from a world unimaginably close, yet forever separate. A world that exists right alongside our own. This is not the realm of fantasy or fiction, not anymore. It is a question that has crawled out from the domain of philosophy and is now being asked in the most hallowed halls of theoretical physics. Is our universe solitary, or is it just one page in a vast cosmic library, one bubble in an infinite effervescent foam of creation? The search for this answer leads us to the very edge of comprehension, to the foundational nature of existence itself, and the evidence we're finding, subtle and strange, is painting a picture of reality so vast and terrifyingly complex it threatens to shatter everything we thought we knew about our place in the cosmos. For millennia, humanity has looked up at the night sky and believed it to be the entirety of the stage. Our stories, our gods, our very meaning were played out under this single, magnificent celestial dome. Ancient philosophers speculated about other worlds, but these were typically planets within our own heavens, or ethereal realms of spirit, not concrete, physical realities coexisting with ours. Our universe was unique, a singular creation. This deeply comforting idea of a special solitary existence was woven into the very fabric of our religions, our cultures, and eventually our science. Even with the Copernican revolution, which displaced Earth from the centre, the universe itself remained the one and only arena of being. But in the early 20th century, a seismic shift began. Our explorations turned from the infinitely large to the impossibly small, and what we found in the subatomic realm was not a miniature clockwork model of the cosmos, but a world of phantoms and probabilities, a domain governed by rules so bizarre, so contrary to all human intuition, that they sounded like the ravings of a madman. This was the dawn of quantum mechanics, and it was here, in the ghostly dance of particles, that the first, truly scientific seed of another universe was planted. To understand this radical departure, we must venture into one of science's most famous and perplexing thought experiments, Schrödinger's cat. Conceived in 1935 by the Austrian physicist Erwin Schrödinger, it was not an experiment he ever intended to perform. It was a parable, a stark illustration designed to expose the sheer absurdity of where the new quantum theories were leading. Imagine a sealed, soundproof box, completely opaque to the outside world. Inside this container we place a cat. Alongside the feline we position a strange diabolical device. It consists of a single radioactive atom, a Geiger counter, a hammer, and a small vial of deadly poison. The radioactive atom is governed by the laws of quantum mechanics. This means its decay is a fundamentally probabilistic event. Over the course of 1 hour, let's say there is a precise 50-50 chance that this atom will decay. If it does decay, the Geiger counter will detect the radiation. This detection will trigger the hammer. The hammer will then swing down, shattering the vial of poison. The release of the poison will tragically kill the cat. If the atom does not decay, none of this happens and the cat remains alive. We seal the box and wait for 1 hour. At the end of that hour, without opening the box, we ask a simple question. Is the cat alive or dead? Our common sense, our entire experience of the macroscopic world, screams that the answer is one or the other. The cat is either living or it is deceased. We just don't know which one yet. But this is not what the mathematics of quantum mechanics described. According to the standard interpretation of the time, the atom itself exists in an indeterminate state, a superposition. It has not yet made a choice. It is simultaneously decayed and not decayed. Because the entire system inside the box is linked to the state of that atom, the Geiger counter is both triggered and not triggered. The hammer is both fallen and not fallen. The poison is both released and contained. and therefore the cat, bound by these quantum chains, is in a superposition of states. It is both alive and dead at the same time, a ghostly paradoxical fusion of two mutually exclusive realities. Schrödinger found this conclusion utterly preposterous. A cat cannot be both alive and dead. He intended this paradox to show a flaw in the theory. But what if the theory was right? The standard explanation, known as the Copenhagen interpretation, argued that this bizarre superposition only lasts until a measurement is made. The moment we open the box and observe the system, reality is forced to choose. The wave function, as it's called, collapses. In that instant, one possibility becomes real, and the other vanishes forever. We see either a living cat or a dead one. But this raised a profoundly troubling question. What constitutes an observation? Does it require a conscious human? A camera? Does the cat itself count? The theory was silent, and it placed the observer in a privileged, almost godlike role, conjuring reality out of probability simply by looking. For decades, this was the uneasy status quo. Then, in the 1950s, a brilliant, audacious young graduate student at Princeton University named Hugh Everett III looked at the same equations and proposed a different, even more mind-bending solution. He suggested that the wave function never truly collapses. Reality is never forced to make a choice. When the moment of decision arrives for that radioactive atom, the universe itself splits in two. In one universe, the atom decays, the poison is released, and the cat dies. In another, parallel universe, the atom does not decay, and the cat remains blissfully unaware, alive and well. Every single quantum event, happening trillions upon trillions of times every second across the cosmos, is a branching point, a fork in the cosmic road. Everett's idea, which came to be known as the many worlds interpretation, was not born of a desire for science fiction. It was born from taking the mathematics of quantum theory at its most literal, unvarnished value. The equations themselves suggested this continuous exponential splitting. There was no need for a magical collapse, no special role for an observer. The theory was elegant, simple, and utterly terrifying in its implications. It meant that for every choice you have ever made, every path you didn't take, a version of you in another universe took it. There is a universe where you accepted that other job, a universe where you boarded that plane you missed, a universe where you said yes instead of no. An uncountable, an infinite number of parallel realities, each one as real as our own, branching away from us with every passing moment. Our life is not a single thread, but an infinitely branching tree. At the time, Everett's theory was met with ridicule and dismissal. The physics community, including the great Niels Bohr, could not accept the sheer ontological extravagance of it. The idea of creating entire universes with every subatomic interaction was too much to bear. Discouraged, Hugh Everett left academia and spent the rest of his career doing classified defense work. He had looked into the abyss of quantum reality and reported what he saw, and the world had refused to listen, but his idea did not die. Decades later, as physicists grappled with the deepening mysteries of quantum mechanics and cosmology, the many worlds interpretation was resurrected. It offered a potential solution to so many paradoxes that, for a growing number of today's leading physicists, it is now considered the most likely description of the reality we inhabit. Our universe is not alone. It has countless companions, born from the ceaseless churn of quantum chance. This quantum genesis of other universes is deeply unsettling, but it is primarily a theoretical framework. It emerges from the equations that describe the subatomic world. But is there any evidence for other universes on a grand cosmic scale? To find it, we must journey back in time to the very dawn of creation. We must examine the faintest, oldest light in the cosmos, the cosmic microwave background, or the CMB. Imagine the universe just 380,000 years after the Big Bang. It was not a place of stars and galaxies, but a searing, opaque fog of superheated plasma. A roiling soup of protons and electrons, so dense that light could not travel freely. It was trapped, bouncing endlessly between charged particles like a ball in a pinball machine. But as the universe expanded, it cooled. Eventually it reached a critical temperature where protons and electrons could finally combine to form the first neutral hydrogen atoms. In that moment, the universe suddenly became transparent. The light that had been trapped for eons was set free, and it began a journey across the cosmos that would last for 13.8 billion years. That ancient light is still washing over us today. It arrives from every direction in the sky, cooled by the expansion of space to a faint, cold glow, detectable only by our most sensitive radio telescopes. This is the cosmic microwave background. It is the afterglow of creation, a baby picture of our universe. And when we look at that picture, it is breathtakingly uniform. The temperature is almost perfectly the same everywhere we look, a testament to the incredible smoothness of the early cosmos. Almost perfect, but not quite. Dotted across this ancient tapestry are minuscule variations in temperature, tiny ripples that represent the seeds of all future structure. The slightly hotter, denser regions would, over billions of years, gather matter through gravity to form the galaxies, stars and planets we see today. Our models of the Big Bang and cosmic inflation predict the statistical distribution of these hot and cold spots with stunning accuracy. Our theories match the observed data almost perfectly. Almost. Because in this otherwise pristine photograph of the infant universe, there is something that shouldn't be there. A colossal anomaly. First detected by NASA's DUDMAP satellite in 2004 and later confirmed by the more powerful Planck satellite, it is a region of space in the constellation Eridanus that is unnervingly, inexplicably cold. This is not just another cold spot. It is vast, spanning over 1 billion light-years. And it is significantly colder than our best cosmological models can account for. The probability of such a cold patch appearing by random chance is staggeringly low, less than 1%. It is an outlier so significant that it has been given a simple, ominous name, the cold spot. For years, cosmologists have struggled to explain it. Perhaps it is some unknown instrumental error, though multiple independent observations make this unlikely. Perhaps it is caused by a supervoid, an enormous region of space between us and the CMB that is unusually empty of galaxies, which could create a slight cooling effect on the light passing through. Surveys of that region have indeed found a void, but it is not nearly large enough or empty enough to account for the full extent of the observed coldness. The mystery endures, and this has led some scientists to a truly shocking and speculative hypothesis. What if the cold spot is not a feature of our universe, but evidence from another? This idea comes from a theory known as eternal inflation. The standard Big Bang model describes our universe beginning from a singularity. Eternal inflation theory suggests that our Big Bang was not a unique event. Instead, imagine a vast, overarching metaspace, a bulk that is eternally and rapidly expanding, or inflating. Within this inflating bulk, quantum fluctuations can cause small patches to suddenly stop their rapid expansion and cool down, forming a bubble. Each of these bubbles becomes a universe, like ours. Think of it like a gigantic pot of water coming to a boil. The boiling water is the inflating metaspace, and the bubbles of steam that form within it are individual universes. New bubbles are constantly forming, each one potentially giving rise to its own Big Bang, its own set of physical laws, its own destiny. In this scenario, our universe is but one bubble in an infinite cosmic ocean of bubbles. And just like bubbles in a pot, these universes could, on rare occasions, collide. If another bubble universe bumped into our own in the distant past, it would have left a mark. The collision would have dissipated energy, creating a kind of cosmic shockwave that would ripple through the fabric of our young universe. This impact would leave behind a distinct signature in the cosmic microwave background, a vast, circular, slightly colder region, a cosmic bruise. The cold spot in Eridanus matches the predictions of such a collision with an eerie degree of accuracy. This is no longer just mathematics or abstract theory. This is a tangible, observable anomaly in the sky. It's a potential scar from an encounter with another reality, a piece of evidence, written in the oldest light in existence, suggesting that we have touched another world. The implications are staggering. If this interpretation is correct, it confirms not only that other universes exist, but that they can interact. that the membrane of our reality is not entirely impermeable. This leads us to yet another frontier of theoretical physics, one that provides a potential architecture for how such a multiverse might be structured: string theory. For decades, physicists have been on a quest for a theory of everything, a single, elegant mathematical framework that can unite the two great pillars of modern physics: Einstein's general relativity, which describes gravity and the universe on a large scale, and quantum mechanics, which describes the other forces on a small scale. The most promising and most controversial candidate for this ultimate theory is string theory. String theory proposes a radical new picture of fundamental reality. It suggests that the elementary particles we observe, electrons, quarks, photons, are not point-like dots. Instead, they are the different vibrational modes of a single underlying object, a tiny, one-dimensional, oscillating filament of energy called a string. Imagine a violin string. By plucking it in different ways, you can produce a variety of different musical notes. In the same way, according to string theory, a fundamental string vibrating in one specific pattern would manifest to us as an electron. Vibrating in another pattern, it would appear as a photon. A different vibration still, a quark. All the matter and all the forces of nature are nothing but the different notes played on these infinitesimally small cosmic strings. It is an idea of breathtaking beauty and simplicity, all the richness and complexity of the universe emerging from one single entity. But for the mathematics of string theory to work, for it to be consistent, it makes an extraordinary demand. It requires that the universe does not just have the three dimensions of space, length, width, height, and one of time that we are familiar with. It requires the existence of at least 10, or in some versions, 11 dimensions. So where are these other dimensions? Why can't we see them? The theory suggests they're curled up, compactified into a space so small, far smaller than an atom, that they're completely invisible to us. Imagine a long, thin garden hose. From a great distance, it looks like a one-dimensional line, but for an ant walking upon its surface, it clearly has a second dimension, the circular path around the hose's circumference. In a similar way, these extra dimensions could be all around us, but their geometry is so minuscule that we simply cannot perceive them. This idea of hidden dimensions opened the door to an even more profound concept. An evolution of string theory known as M theory posits that our entire three-dimensional universe might exist as a surface, or a membrane, floating within a higher dimensional space. This is the concept of a brane. Picture our universe as a single, vast sheet of paper. Everything we know, every star, every galaxy, every person is confined to this sheet. We can move up, down, left, and right, but we cannot leave the surface of the paper. Now, imagine another sheet of paper, another brane universe floating parallel to ours, perhaps only a millimeter away in that higher unseen dimension. It could be right here, right now, occupying the same space but shifted in a dimension we can never access. It would have its own stars, its own galaxies, and potentially its own versions of life. We would be completely unaware of its existence and it of ours. We would be like two parallel pages in a closed book, infinitesimally close, but never touching. In this Brane World scenario, most forces and particles, the very stuff of our reality, are tied to our brain like ink on the page. They cannot leave it. But there is one fundamental force that string theory suggests might be different: gravity. Unlike the other forces, gravity is not caused by the vibration of an open-ended string tied to our brain. It is produced by a closed loop of string, and these closed loops are not confined to our membrane. They are free to travel between the branes, leaking across the higher dimensional space. This offers a tantalizing potential explanation for one of physics' greatest mysteries. Why is gravity so incredibly weak compared to the other fundamental forces? The electromagnetic force between two protons is a trillion times stronger than their gravitational attraction. Perhaps gravity isn't inherently weak. Perhaps its full strength is being diluted, spread out across all the parallel branes and extra dimensions. We are only feeling a faint residual whisper of its true power leaking over from the bulk. This idea is not just a philosophical musing. it makes testable predictions. If there are other branes very close to our own, gravity might behave in strange ways at very small sub-millimeter scales. Physicists at places like the Large Hadron Collider are actively searching for evidence of these extra dimensions. They are smashing particles together at incredible energies, hoping to see signs of energy leaking away from our brane into the bulk, carried off by gravitons, the hypothetical particles of gravity. Finding such evidence would be a monumental discovery. It would prove the existence of dimensions beyond our own and provide the strongest support yet for a multiverse of branes stacked like cosmic layers right beside us. We stand at a precipice in human understanding. We have three distinct, yet potentially interconnected lines of scientific inquiry, all pointing toward the same radical conclusion. From the quantum world, the many worlds interpretation suggests that reality is constantly splitting into a tree of parallel universes. From cosmology, the theory of eternal inflation posits a foam of bubble universes, with the CMB Cold Spot as a possible scar from an ancient collision. From fundamental theory, M-theory provides an architecture of brane worlds, existing parallel to our own in higher dimensions. Each of these ideas is on the cutting edge of science. Each is controversial, but together they form a compelling, convergent narrative. The idea of a solitary universe is beginning to look less like a certainty and more like a failure of imagination. The philosophical and existential weight of this paradigm shift is immense. If the multiverse is real, what does it mean for our sense of self? If there are infinite versions of you, each living out a different life, which one is the real you? Are you merely the sum of all your possible selves? It challenges our notions of free will and consequence. If every decision you make simply creates another branch of reality where you made the opposite choice, does that diminish the weight of your actions? Or does it amplify them, creating a cascade of new worlds with every thought? It could mean that anything that is not forbidden by the laws of physics is not just possible, but is actually happening somewhere. In some universe, the dinosaurs were never wiped out. In another, humanity has already colonized the stars, and in yet another, perhaps life never began on Earth at all. This is the ultimate Copernican revolution. Not only are we not the center of our solar system, or our galaxy, or even our universe. We may not even exist in the only universe. Our entire cosmos, all 13.8 billion years of its history, and all its 100 billion galaxies, could be just one insignificant grain of sand on an infinite cosmic shoreline. It is a humbling, and for some, a terrifying realization. It can feel as though it strips our lives of meaning and significance. But perhaps the opposite is true. Perhaps the knowledge that countless versions of our story are playing out gives us a greater responsibility to make this branch, our branch, the best it can be, to cherish its uniqueness, its specific series of improbable events that led to our existence, right here, right now. The search for definitive proof continues. Astronomers are scanning the cosmic microwave background with ever greater precision, looking for more bruises, more evidence of cosmic collisions. Particle physicists are pushing their accelerators to higher and higher energies, hunting for the shadows of extra dimensions. And quantum theorists are designing new experiments to test the foundational assumptions that separate the world of many worlds from the world of a single reality. We do not yet have the final answer. We may not have it for a century or ever. We are like ancient mariners who have just realized the ocean is far larger than they ever dreamed, and have seen what looks like the faint outline of a new continent on the distant horizon. Is it real, or a mirage? We don't know for sure, but we have set sail. The journey into the multiverse has begun, so the next time you experience that strange feeling of déjà vu, or catch a fleeting shadow in the corner of your eye, pause for a moment. Allow yourself to wonder. Perhaps you're not just remembering, but resonating with another version of yourself. Perhaps it is not a trick of the light, but the faintest gravitational ripple from a world just a dimension away. We live on a membrane of reality, floating in an ocean of possibility, unaware of the countless other worlds that may lie just beyond the veil. The universe is not what we thought it was. It is infinitely larger, infinitely stranger, and infinitely more mysterious. And we are just beginning to open our eyes. In the theater of your mind, you have already broken the law. You have commanded starships with hulls of impossible alloys, ships that slice through the interstellar medium like a thought. You have seen the swirling arms of a galaxy you do not call home, watched twin suns set over a world of crimson deserts, and charted courses through the ghostly tendrils of dying nebulae. This dream is not new. It is a primal echo, a story we have told ourselves for generations. It whispers from the pages of our oldest myths and screams from the screens of our most ambitious fantasies. The dream of the voyage, the longing for the beyond, the innate unshakable human impulse to pack up our existence, to leave the shores of the known, and to sail across the greatest ocean of all. We have drawn the maps. We have named the destinations. Proxima Centauri, our nearest stellar neighbour, a mere 4 light-years away. A journey our fastest probes today would take 70,000 years to complete. In our dreams, we make the trip before breakfast. We imagine stepping onto a world orbiting that faint red star, feeling a different gravity beneath our feet, breathing an atmosphere born of a different chemistry. We see ourselves pushing further to the trapezium cluster in Orion, a stellar nursery where infant suns are swaddled in incandescent gas. We envision humanity building outposts among the Pleiades, those 7 sisters shimmering like a cluster of celestial diamonds. And in our boldest visions we cross the chasm, 2.5 million light-years of cold, empty intergalactic space to arrive at the majestic spiral of Andromeda, a city of 1 trillion stars, an empire of worlds to explore. This ambition is woven into our very essence. It is the same spirit that drove our ancestors across continents, the same yearning that pushed explorers over the horizon of unknown oceans. The cosmos is simply the final grandest frontier. Its scale is an invitation, a challenge thrown down by existence itself. From our quiet perch in a tranquil spiral arm of the Milky Way, we look out into a universe of 2 trillion other galaxies, each one a repository of hundreds of billions of suns, each sun a potential anchor for new worlds, new life, new beginnings. The sheer volume of reality is staggering, almost insulting in its immensity. It seems to demand that we participate, that we bear witness. This vastness makes our dream of rapid transit not merely a desire but a profound existential necessity. To remain tethered to this one small blue world forever feels like reading only the first word of an epic masterpiece. We want to read the whole story. We need to know what happens next, and so we build the ships of our imagination, vessels powered by contained singularities or shimmering antimatter drives. We see them gathering in orbit, their crews bidding farewell, their mission to leap across the cosmic chessboard in a single glorious move. The countdown ends. The engines ignite with silent, terrible force. The journey begins. The ship accelerates, pushing ever faster, chasing the most elusive prize in the universe. It is a velocity of pure magic, a speed that turns distance into an afterthought. 186,000 miles per second. 300 million meters every single tick of the clock. The speed of light. And it is here at the very threshold of our greatest aspiration that we collide with a wall. It is not a wall of matter or energy. It is a wall woven from the fundamental logic of the universe. A barrier built into the fabric of space-time itself. You see, the universe is governed by laws. Laws of gravity, of thermodynamics, of electromagnetism. But there seems to be one law that precedes all others. One ultimate inviolable commandment that underpins everything. And that commandment is this: thou shalt not travel at the speed of light. Not you, not your starship. Not any object anywhere in the cosmos that has even a single atom of mass. This cosmic speed limit, the constant we call c, is absolute. It is not a technological hurdle we can one day overcome. It is not an engineering problem awaiting a clever solution. It is a fundamental feature of reality as we know it. It is the universe looking at our grandest dream and saying simply no. So the question, the great and frustrating question is, why? Why does the universe care how fast we move? What is so special about this particular velocity? Why isn't it just a little bit faster or a little bit slower? And what truly happens in that strange forbidden territory as you get closer and closer to that ultimate impossible speed? The answer is not intuitive. It defies our everyday experience. It will force us to abandon our most deeply held assumptions about space, about time, and about the very nature of what it means to be real. To understand this barrier, we cannot simply look to engineering. We must look to the architecture of existence itself. Our first instincts are to blame our tools. Surely we just need a more powerful engine, more efficient fuel, a more streamlined design. We are a species of builders. We solve problems by building better machines. If our cars are too slow, we build supercars. If our planes are too slow, we build jets that break the sound barrier. Each time we encounter a limit, we have engineered our way past it. So our minds naturally leap to this conclusion again. We imagine a future where some brilliant breakthrough in propulsion finally gives us the necessary thrust to reach light speed. We picture a power source so immense it could drain a star funneled into an engine that could punch a hole through the void. But the universe does not yield to brute force. The problem isn't the engine. The problem is you. The problem is the ship. The problem is the very fact that you exist as matter. Imagine you are on a cosmic highway in the most advanced vehicle ever conceived. You press the accelerator. You rocket forward from 1,000 to 1,000,000 to 10 million miles per hour. From our earthbound perspective, your progress is astonishing. You cross the orbit of the moon in minutes. Mars flashes by. Jupiter, with its swirling, storm-racked eye, dwindles in your rearview mirror. You feel the immense power, the glorious, liberating speed. But something strange begins to happen. For every gallon of fuel you burn, you get less and less acceleration in return. The accelerator feels heavier. The ship seems to resist your command. It's as if you were driving into a cosmic headwind, one that grows exponentially stronger the faster you try to go. To get from 0 to 50% of light speed is a monumental task, but to get from 90% to 91% requires far more energy. To go from 99% to 99.1% demands an almost ludicrous and almost infinite amount of power. The universe is actively fighting you, working against you. It is imposing a law of diminishing returns so severe it amounts to an absolute prohibition. It's as if you are running in a dream, pumping your legs with all your might, only to find yourself moving in slow motion. The finish line, the speed of light itself, never actually gets any closer. It recedes from you, an ever-distant, shimmering mirage. You can approach it. You can get tantalizingly, infinitesimally near, but you can never, ever touch it. So what is this cosmic friction? What is this force of resistance? It is not a force at all. It is a whisper from the deepest truths of the universe. A whisper that tells us mass and energy are two sides of the same coin. A whisper made famous by the most elegant equation ever written, E equals mc squared. This small, unassuming statement is the secret gatekeeper. It is the mathematical reason our journey to the stars is so difficult. It holds the key to why the cosmic speed limit exists at all. Because that c in the equation, that speed of light, isn't just a number. It is a conversion factor. It is the exchange rate between the currency of matter and the currency of energy. And as your starship accelerates, that equation comes alive. The colossal energy your engines are pouring into the ship, the energy of motion has to go somewhere, and it goes into your mass. You become heavier. The ship, everything on board, begins to gain substance. Not in the sense of adding more atoms, but in the sense of gaining inertia, gaining a profound resistance to any further change in motion. As you approach the speed of light, your mass begins to skyrocket. It balloons towards infinity. And to accelerate an object with infinite mass, you would need an infinite amount of energy. You would need to harness the power of the entire universe, and then some, just to gain that last infinitesimal inch of speed. It is the ultimate paradox. The pursuit of ultimate velocity makes you infinitely massive and therefore impossible to move. The law folds in on itself, creating an impenetrable logical fortress. This isn't speculation. It's not a theoretical quirk. We see this law enforced every single day in our most powerful machines. Inside the vast circular tunnels of particle accelerators, we perform this experiment 1 trillion times a second. We take tiny subatomic particles, protons and electrons, and we use phenomenally powerful magnetic fields to accelerate them. We push them to the very edge of the cosmic speed limit, 99.9999% of the speed of light. They become titans, their effective mass increased thousands of times over. A single proton can strike a target with the kinetic energy of a speeding train. We can pour more and more energy into these accelerators, enough to power entire cities, and the particles get closer to C. They get agonizingly, breathtakingly close, but they have never, not once in all our experiments, reached it. They have never broken this one sacred law. The universe, even on its smallest, most fundamental scale, holds the line. But this only deepens the mystery. If everything with mass is forbidden from reaching this speed, then how does light itself do it? What is so special about a photon, a simple particle of light? The answer is as simple as it is profound. A photon can travel at the speed of light because it has no mass. It is pure energy, pure motion. It is born at light speed, it lives its entire existence at light speed, and it dies at light speed, absorbed by some atom somewhere in the universe. It knows no other way of being. For a photon, there is no such thing as acceleration or deceleration. There is only C. This creates a fundamental division in the universe, a great caste system of existence. There are the things with mass, the stuff of planets, stars, and people, and there are the things without mass, like the photons of light and the gluons that hold atomic nuclei together. One group is forever bound to the slow lane, doomed to exist below C. The other group is forever locked into the cosmic express lane, able to travel only at C. There is no middle ground. There is no crossing over. You either have mass and are slow, or you have no mass and are fast. This is the law, and even this explanation feels incomplete. It feels like a symptom, not the cause. We are still left asking why. Why is reality structured this way? The search for that deeper answer takes us back over a century to the mind of a young patent clerk who dared to ask a simple question. What would you see if you could ride on a beam of light? This was the thought experiment that shattered the old universe. It was the key that unlocked a new and profoundly strange reality. Because what Albert Einstein realized was that the speed of light isn't just a speed limit. It is the one thing in the universe that is constant. It is the one thing that never changes, and that is an idea that should make the hair on your arms stand up. Think about what it means. If you are standing still and you shine a flashlight, the beam of light moves away from you at the speed of light. That makes sense. But now imagine you are in that starship, traveling at 99% of light speed. You shine the same flashlight forward. Our intuition, our everyday common sense, tells us that the light from your flashlight should move away from you at only a tiny fraction of its normal speed. We add and subtract velocities all the time. If you're on a train moving at 50 miles per hour and you throw a ball forward at 10 miles per hour, someone on the ground sees the ball moving at 60. Simple. But light does not obey this rule. Light breaks the rule. Aboard your starship, when you shine that flashlight, you will measure that beam of light moving away from you at exactly 186,000 miles per second. And more astonishingly, someone watching you fly past someone you perceive as being almost stationary will also measure that same beam of light moving at the exact same speed. It is an impossible observation. It is a paradox that seems to break the very foundations of logic. How can two observers moving at vastly different speeds both measure the same photon as moving at the same velocity relative to them? It's like two cars driving in opposite directions, yet both drivers see the same bird flying between them at the exact same speed. It makes no sense. And yet, it is the truth. It has been confirmed by countless experiments. The speed of light in a vacuum is the universe's one true constant. It is the ultimate reference point, the supreme, immovable object. And if the speed of light must remain the same for everyone, for every observer, then something else has to give. Something we thought was rigid and absolute must in fact be flexible. Something has to stretch and shrink and warp to preserve this one bizarre cosmic law, that something is everything else, space and time. This is the heart of the matter. This is the core of Einstein's revelation. Space is not a static, empty stage on which events unfold. Time is not a universal clock ticking at the same rate for everyone. They are a single, unified, dynamic fabric space-time. And this fabric is profoundly pliable. It is this pliability that conspires to prevent you from reaching light speed. As you accelerate in your starship, space-time itself transforms around you. To an outside observer, your ship would appear to be shrinking in the direction of motion. The universe itself would be physically compressing ahead of you. More profoundly, to that same observer, your time would slow down. The clocks on your ship would begin to tick at a different rate than the clocks back on Earth. For every year that passed for you centuries, then millennia could pass for the home you left behind. This isn't a mechanical failure of the clock. It is time itself, the very flow of causality, that is being altered by your motion. And as you approach the speed of light, this effect becomes absolute. From the perspective of the outside universe, your time would grind to a complete halt. A journey to the nearest star could take you a few years subjectively, but you would return to an Earth tens of thousands of years in the future. At the speed of light itself, time ceases to exist. For a photon, the journey from a distant galaxy to your eye is instantaneous. In its own frame of reference, birth and death happen in the same moment. The entire lifespan of the universe, all of 1 billion years, passes for it in no time at all. This is what awaits at the speed of light, the dissolution of time, the convergence of all points in space. It is not a destination, it is a state of being utterly alien to anything with mass. It is a realm of timeless, massless existence that we can perceive but never enter. So the wall that blocks our path is not made of brick and mortar. It is woven from the relationship between mass and energy, and it is mortared together by the very nature of space and time. To travel at the speed of light would require you to become infinitely massive, which would require infinite energy. It would require you to occupy zero space and to exist in a state where time no longer passes. In other words, to travel at the speed of light, you would have to cease being you. You would have to become light. This is the profound and beautiful prison in which we live. The universe gives us this tantalizing glimpse of ultimate speed, this constant sea that dictates the flow of information and causality, and then it builds the rules of physics to ensure we can never attain it. So is the dream dead. Is humanity forever confined to our own cosmic neighborhood, sentenced to journeys that last for generations? Perhaps not. For if the universe is a place of inviolable laws, it is also a place of loopholes. And a species as clever and as stubborn as ours will not stop searching for them. The laws of physics as we know them forbid breaking the light barrier. but they might allow us to bend them, to warp space, to tunnel through it, to find a shortcut where no road exists. But first, we must understand the law we hope to circumvent. We must journey deeper into this strange reality that Einstein revealed, a reality where your speed dictates your experience of time, where motion changes mass, where gravity is not a force but a curvature of space-time. We must understand why c isn't just a speed limit. It's the fundamental beat of the cosmic drum, the rhythm to which all of reality must dance. And by understanding it, we may finally understand our true place in the cosmos, not as masters of the universe, but as clever passengers learning the intricate rules of the road. The journey ahead is one into the very heart of what is real, and it begins with that one simple, impossible observation: the unwavering, incorruptible, and majestic constancy of light. Right now, you are moving at over 1,000 miles per hour. That is the speed of our planet's rotation, a silent, ceaseless waltz. You are also hurtling at 67,000 miles per hour as Earth dutifully makes its annual pilgrimage around the Sunday, and our entire solar system is being dragged through the galaxy at an astonishing 500,000 miles per hour. You feel none of it, because for us, creatures of flesh and instinct, speed is relative. It's a concept we understand only through comparison, through the blur of the landscape outside a train window or the rush of wind against our skin. Motion is the fundamental story of our universe. But the rules of that story, the very laws of motion itself, were once thought to be profoundly, reassuringly simple. They were written down by one man. In the hallowed halls of Cambridge, Sir Isaac Newton dipped his quill and sketched the blueprint for a clockwork universe, a cosmos of magnificent, predictable certainty. His laws of motion were pillars of logic so intuitive they felt less like discoveries and more like common sense carved into the fabric of existence itself. And at the heart of this Newtonian world was a simple, elegant idea, an idea that governs everything from a thrown stone to a cannonball. Imagine you are on a train traveling at 60 miles per hour. Inside your carriage, you throw a ball forward at 20 miles per hour. To an observer standing still on the platform watching you pass, the ball isn't moving at 20 or at 60. It's traveling at 80 miles per hour. Your speed and the ball's speed simply add together. It is a law of accumulation. In Newton's universe, there was no ultimate speed limit, no cosmic barrier. Velocity was a ladder you could climb forever. If you had a powerful enough engine, a long enough journey, you could just keep adding speed, endlessly accelerating. 100 miles per hour, 1,000, 1,000,000, 1,000,000,000. The universe was an infinite raceway with no final finish line. Space was a fixed absolute stage, a rigid three-dimensional grid. Time was a universal metronome, a majestic river flowing at the same relentless pace for every observer everywhere in the cosmos for all of eternity. This was the bedrock of classical physics for 2 centuries. It built empires. It powered the Industrial Revolution. It gave us a sense of mastery over the physical world. It was perfect, it was logical, and it was completely, fundamentally wrong. The first clue that something was deeply amiss in our understanding did not come from the study of motion or planets or gravity. It came from a flicker of light. It emerged from the brilliant mind of a Scottish physicist, James Clerk Maxwell, a man who sought to tame the unseen forces that governed our world: electricity and magnetism. He gathered up the disparate, chaotic discoveries of his predecessors and unified them into a set of 4 breathtakingly beautiful equations. They were a symphony of mathematics, revealing for the first time that electricity and magnetism were not separate phenomena at all. They were 2 sides of the same coin, an intimate, eternal dance between invisible fields. But as Maxwell worked through the implications of his own masterpiece, he discovered something else, a ghost in the machine. His equations predicted that if you disturb these interconnected fields, if you make an electric charge wiggle, it creates a ripple that travels outward, a self-sustaining wave of pure electromagnetic energy. His mathematics didn't just describe this wave, it gave its exact speed, a velocity derived from the fundamental constants of nature itself. The number that fell out of his equations was astounding, roughly 300,000 kilometers per second, 186,000 miles per second. It was a number that had been measured before. It was the speed of light. In a stunning moment of revelation, humanity finally understood what light truly was. Not a particle, not an essence, but a traveling disturbance in the electromagnetic field, a wave of pure energy forever propagating through the void. But this profound discovery concealed a venomous, paradoxical question, a problem so deep it threatened to shatter Newton's entire universe. The speed of light in Maxwell's equations wasn't relative, it was a constant, an absolute. It didn't say the speed of light relative to its source, it just said the speed of light, period. This was a declaration of war against the simple logic of the train. If Newton was right, the speed of a light beam should depend on the motion of the object that created it. If you stood still and turned on a flashlight, light would travel away from you at its characteristic speed. But if you were on a spaceship traveling at half the speed of light and turned on the same flashlight, an observer watching, you should see that beam of light moving at 1.5 times the normal speed of light. Simple addition. It was the law. Maxwell's equations, however, said no. They insisted that no matter how fast you are moving, no matter how quickly the source of the light is traveling, that beam will always be measured to be moving at the exact same unwavering defiant speed. This was an impossible choice, a schism at the heart of physics. Either Newton's foundational laws of motion were wrong or Maxwell's revolutionary theory of electromagnetism was flawed. The scientific community of the late 19th century, unwilling to abandon the Newtonian cathedral, searched for an escape hatch, and they found a clever one. They reasoned that if light is a wave, it must need a medium. Sound waves travel through air, ocean waves travel through water. So light waves must travel through an invisible, undetectable substance that filled every corner of space, every void between the stars. They called it the luminiferous ether. The ether was imagined as a phantom material, massless, frictionless, perfectly transparent, yet more rigid than steel. It was the absolute, motionless backdrop of the cosmos, the stage upon which all cosmic events unfolded. Suddenly, the problem of light's constant speed seemed solved. Maxwell's equations, they argued, must describe the speed of light relative to this stationary, all-pervading ether. This was a neat and tidy solution, and it offered a tantalizing historic opportunity. For if this ether existed, and the Earth was orbiting the Sun, then our planet must be constantly ploughing through this substance. We should be flying through a perpetual invisible ether wind. Just as you feel the wind on your face when you ride a bicycle, we should be able to detect our motion through the ether. We should be able to measure our absolute speed through the universe. All someone had to do was build a device sensitive enough to catch this cosmic ghost. That task fell to two American scientists, Albert Michelson and Edward Morley. They were masters of precision, virtuosos of experimental physics. In 1887, they constructed one of the most elegant and sensitive instruments ever conceived to hunt for this ethereal wind. It was called an interferometer. Its design was a masterpiece of ingenuity. A beam of light was split in two by a partially silvered mirror. The two beams were sent on perpendicular journeys of equal length, bounced off other mirrors, and then recombined. The principle was simple. If the Earth was moving through the ether, one beam of light would be traveling against the ether wind, and then with it, the other would be traveling across it. The journey across the wind would be slightly faster. When the two beams of light were brought back together, this tiny difference in travel time would cause their waves to be slightly out of sync. They would interfere with each other, creating a distinctive pattern of light and dark fringes. By rotating the entire apparatus, they could change the orientation of the light beams relative to the ether wind, and they should see this interference pattern shift. The device was a delicate trap for a phantom. To shield it from even the most minuscule vibrations, it was built on a massive sandstone slab floating in a pool of liquid mercury. It was an experiment of almost unimaginable precision, capable of detecting a shift far smaller than the one predicted. Michelson and Morley held their breath. They aligned their mirrors. They rotated the heavy slab with painstaking care. And they watched, and they saw absolutely nothing. The interference pattern did not shift, not by a fraction. Not at all. It was as if the ether wind did not exist. They rechecked their calculations. They refined their experiment. They tried again, at different times of day, at different times of the year when the Earth's velocity should be pointing in a different direction in space. The result was always the same. Utter, confounding silence. The light beams stubbornly refused to cooperate. They always returned to the detector at the exact same instant, as if the journey against the wind and across it took identical amounts of time. It was a perfectly designed, flawlessly executed experiment that delivered the single most catastrophic result in 19th century physics. The prime suspect in the case of light's constant speed, the ether, had a perfect, unshakable alibi. It simply wasn't there. Science had reached a profound, terrifying impasse. The evidence was undeniable, the speed of light was a constant, but the theoretical framework to explain why did not exist. The elegant clockwork universe of Isaac Newton was broken. The laws that had governed science for 200 years were cracking under the strain of a single obstinate fact. Physics needed a hero, a revolution, and it found one not in a grand university laboratory, but in a quiet patent office in Bern, Switzerland. His name was Albert Einstein. He was not a celebrated professor. He was a clerk, a young man whose job was to examine the inventions of others. But in his mind, he was soaring through the cosmos, wrestling with the deepest questions of existence. He was haunted by the paradox of light. This contradiction between Newton's world of relative motion and Maxwell's world of absolute light speed. Unlike his contemporaries who tried to patch the old theories to find some new exotic property of matter to explain the null result, Einstein decided to start from a place of radical acceptance. He asked a different kind of question. What if the experiment wasn't wrong? What if the universe was truly this strange? What if the constancy of the speed of light wasn't the problem to be solved, but the fundamental clue to a new, deeper reality? He began to conduct experiments, not with mirrors and mercury, but with the most powerful instrument. He possessed his own imagination. He called them Gedankenexperimenten, thought experiments. And one of them, a question he first asked himself as a teenager, would change the world forever. It is a question you can ask yourself right now. What would you see if you could race alongside a beam of light, matching its speed exactly? What would the universe look like from the saddle of a photon? According to the old laws of Newton, the answer is simple. The light wave would appear to you to be completely stationary. It would be frozen in space next to you. A shimmering, static, oscillating wave of electric and magnetic fields suspended in eternal stillness. But to the young Einstein, this vision was a logical nightmare. It was a deep and catastrophic violation of physics. Because according to Maxwell's own equations, the very laws that defined light, a frozen light wave, cannot exist. Light is a self-propagating disturbance. Its changing electric field creates a magnetic field. Its changing magnetic field, in turn, creates an electric field. It is this ceaseless regenerating dance that allows it to travel. A static light wave is a contradiction in terms, an impossibility. It would be like finding a sound wave that doesn't vibrate or an ocean wave that doesn't move. It breaks its own definition. Here was the heart of the conflict laid bare in a single image. Newton's laws of motion allowed you to catch up to a light beam and see it frozen. Maxwell's laws of electromagnetism insisted that such a thing could never happen. One of them had to yield. One of these two titanic pillars of physics had to fall. And in a moment of pure genius, in an act of breathtaking intellectual courage, Einstein made his choice. He threw away 200 years of established physics. He abandoned the comforting intuitive logic of Isaac Newton. He decided to trust the paradox. He decided to believe the unbelievable. He proposed two simple radical postulates. First, that the laws of physics are the same for all observers in uniform motion. There is no absolute privileged frame of reference. The phantom ether was banished from reality forever. And second, the postulate that would tear down our reality and build a new one in its place. The speed of light in a vacuum is the same for all observers regardless of their motion or the motion of the light source. It is the one true cosmic constant. An inviolable absolute law. This was not a solution. It was a declaration, a statement that the universe is fundamentally stranger than we had ever dared to imagine. But if this declaration is true, if the speed of light is the one thing the universe refuses to change, then to preserve that constancy, something else must give. Something we thought was absolute must in fact be flexible. Einstein realized that to protect this one sacred cosmic law, the universe must be willing to sacrifice its very foundations, space itself, and time itself. If the speed of a light beam is constant, no matter how fast you are moving, then your measurement of distance and your experience of time must change to ensure that it remains so. It was a conclusion so bizarre, so contrary to every human experience that it seemed like madness. It meant that for a person moving at high speed, time itself literally slows down relative to a stationary observer. Their clocks tick slower, their hearts beat slower, they age less. It meant that for that same person, space itself in the direction of motion contracts. It shrinks. Rulers become shorter. Distances become compressed. The rigid, absolute stage of Newton's universe was gone. In its place was a new dynamic, interconnected reality, a four-dimensional fabric called space-time, a malleable, elastic medium that could stretch and warp, bend and slow down, all in service of one supreme directive: the speed of light shall not be broken. This was the dawn of special relativity. It was the beginning of the end for our dreams of infinite speed. The simple act of observing a flicker of light had revealed not a simple wave, but a fundamental limit, a boundary woven into the very geometry of the cosmos. The universe did, after all, have a speed limit, and that limit wasn't just a barrier for matter, it was the very thing that defined the relationship between space and time, the source code of reality itself. The question was no longer if we could break this barrier. The question was now, why is it so absolute? What profound truth about existence does this cosmic speed limit protect? And what happens when you try to approach it? The universe is playing a trick on you. Every second that ticks by every meter of space you cross is part of a grand cosmic illusion. For centuries we navigated this illusion with a simple map drawn by the hand of Isaac Newton. A universe of absolute certainties, where space was a rigid, unchanging stage, and time was a universal clock ticking at the same rate for everyone and everything everywhere. It was a clockwork cosmos, predictable and sane. But at the close of the 19th century, a ghost appeared in that magnificent machine. A deep contradiction, a crack in the very foundation of physics had begun to show. The laws that governed motion and gravity Newton's domain could not be reconciled with the new laws of light and magnetism. One set of rules worked perfectly for a thrown ball, the other worked perfectly for a beam of light. But together they produced nonsense. They described a universe at war with itself. Physics had reached a profound impasse, a cosmic crime scene with two perfect opposing truths. And the detective who would solve this impossible case was not a revered professor in a grand university, but a young clerk in a Swiss patent office. A man who dared to ask a simple, childlike question: what would you see if you could ride on a beam of light? His name was Albert Einstein, and to solve the riddle, he would have to tear down our reality and build a new one in its place. He didn't begin with complex equations or grand experiments. He started with two simple, elegant assumptions, two postulates that seemed almost self-evident, but hidden within them was a universe more strange, more flexible, and more fantastic than anyone had ever dared to imagine. His first postulate was an idea of profound democracy. He called it the principle of relativity. It states that the laws of physics are the same for everyone who is not accelerating. It doesn't matter if you are standing still on a planet or coasting through the void in a starship at a constant speed. Your reality is just as valid as anyone else's. Imagine yourself inside a perfectly smooth spacecraft with no windows drifting through empty space. Could you perform any experiment to prove you were moving? If you tossed a ball, it would arc through the air normally. If you poured a glass of water, it would fall straight down. Every interaction, every physical law would behave precisely as if you were motionless in your living room. There is no up or down in the cosmos. And Einstein declared there is no absolute stillness either. All steady motion is relative. This was a beautiful extension of an old idea from Galileo. It felt comfortable. It felt like common sense. It was the calm before the storm. Because Einstein's second postulate was an act of cosmic rebellion, it was a statement so bizarre, so contrary to all human experience, that it should have been impossible. He proposed that the speed of light in a vacuum is constant. It is the same for all observers regardless of their own motion. Think about what this means. If you are standing by the side of a road and a car passes you at 50 kilometers per hour, and the driver throws a baseball forward at 10 kilometers per hour, you would see that baseball moving at 60 kilometers per hour. Simple addition. It's how our world works. But light breaks the rules. Now imagine that same car, but this time the driver turns on a flashlight. The light streams out at its own phenomenal pace, nearly 300 million meters per second. Common sense dictates that you, the roadside observer, should see that light traveling at the speed of the car plus the speed of light itself. But you don't. You measure its speed. And you find it is moving at exactly unalterably the speed of light. Now an astronaut screams past you in the opposite direction, traveling at half the speed of light. She also measures the speed of that flashlight beam. She should see it moving incredibly fast, her speed added to its own. But she doesn't. She finds it is moving at precisely the speed of light. It is the universe's one constant. Its one absolute, unyielding truth. A cosmic speed limit that nothing and no one can alter. It is a symphony with a single, unchanging note heard at the same pitch by everyone, no matter how fast they are rushing toward or away from the orchestra. This single, beautiful, terrifying idea shattered Newton's clockwork. Because if the speed of light must remain constant for everyone, then something else, something we thought was fundamental, must be willing to bend. Something has to give, and that something is time itself. This is the moment our journey toward the stars becomes a voyage into the surreal, the moment we discover that the price of approaching light speed is the distortion of reality, and the first toll is paid in the currency of duration. If you and I are moving relative to one another, our clocks will not agree. My second will no longer be your second. This isn't a mechanical flaw in the clocks. It is a fundamental property of the universe. Time itself is personal. It is elastic, and the faster you move through space, the slower you journey through time from the perspective of a stationary observer. This effect is called time dilation, the stretching of moments. To understand why, we must picture a clock of pure light. Imagine two perfect mirrors facing each other. A single particle of light, a photon, bounces between them. Every time the photon strikes a mirror, the clock ticks. If this clock is sitting still in front of you, the photon travels a straight, simple path up and down. Tick, tock, a steady, reliable rhythm. Now let's put that same clock on a speeding starship. From the perspective of someone on board, nothing has changed. The photon still travels that simple up and down path. The clock ticks away normally. The laws of physics are the same. But for you watching this ship race past, the picture is entirely different. You see the clock moving horizontally across your field of view. For the photon to travel from one mirror to the other, it can no longer go straight up and down. The bottom mirror moves forward before the photon can reach the top one. So the photon must travel a longer diagonal path, and then another diagonal path to catch up with the bottom mirror again. Here is the cosmic puzzle. We see the photon traveling a greater distance. But Einstein's unbreakable second rule states that the speed of that photon must be exactly the same for us as it is for the person on the ship. How can something travel a longer distance at the same speed without taking more time? It can't. From our perspective, the moving clock must tick slower. Each tick, each journey of that photon literally takes longer. The faster the ship moves, the longer that diagonal path becomes, and the more sluggishly its time appears to flow. If that ship could reach the speed of light, the photon's path would become infinitely long. Time for that clock, as seen by us, would stop completely. This is not a thought experiment. It is a physical reality. Every particle accelerator on Earth is a time machine. Tiny subatomic particles are accelerated to 99.99% of the speed of light. And their internal clocks, their rates of radioactive decay, slow down by thousands of times, just as Einstein predicted. The GPS satellites orbiting high above your head are moving much faster than you are. Their onboard atomic clocks tick just a tiny fraction slower than clocks on the ground. If engineers didn't constantly correct for this temporal distortion, the entire global positioning system would fail within hours, accumulating errors of kilometers per day. We are all caught in our own personal currents in the river of time, and the speed of our motion through space dictates the flow. The implications are staggering. It gives rise to the famous twin paradox. Imagine two twins. One stays on Earth, while the other embarks on a fantastic journey to a nearby star traveling at nearly the speed of light. For the astronaut twin, the years pass comfortably. The ship's clocks run normally. She eats, sleeps, and ages at a perfectly ordinary rate. But back on Earth, her twin is watching through a cosmic telescope. He sees his sister's clock and her life unfolding in slow motion. When the traveler returns, decades might have passed on Earth. Her twin brother would be an old man, or perhaps long gone, but she would have aged only a few years. She has time traveled into the future. She didn't break the speed of light. Instead, the speed of light broke time for her. It warped the very fabric of duration to preserve its own constancy. This is the first great barrier to high-speed travel. It's not just an engineering problem of propulsion. It is a fundamental desynchronization with the rest of the cosmos. To travel to the stars is to become a ghost in your own time, to sacrifice your own present for a glimpse of a distant future. But the universe's conspiracy to protect its speed limit doesn't stop with the manipulation of time. If time can be stretched and made malleable, what about space? If the speed of light is a ratio of distance divided by time, and we've already established that time is flexible, then distant space itself must also be pliable. It has to be. This second consequence is known as length contraction. As an object approaches the speed of light, its length in the direction of its motion, as measured by a stationary observer, appears to shrink. Let's return to our starship on its incredible journey. The crew plans to travel to a star 10 light-years away. From the perspective of mission control on Earth, the ship accelerates to 99% of the speed of light. Time on board the vessel slows to a crawl. The journey for the crew takes only a fraction of the expected time. But how does the crew experience this? For them, time is flowing perfectly normally. Their hearts beat once per second. Their clocks tick as they should. If their journey is to be shorter, but their clocks are normal, there is only one possible explanation from their point of view. The distance to the star must have shrunk. The 10 light-years of empty space have contracted before them. The universe has foreshortened itself in their direction of travel. It's a breathtaking concept. Space is not a static void, but a dynamic medium that compresses in response to high-velocity movement. From the outside, we see the ship itself becoming flattened. A sphere would become an ellipsoid. A long, elegant vessel would appear squashed like a photograph squeezed from the sides. The faster it moves, the more pronounced the contraction. At the speed of light, its length in the direction of motion would shrink to zero. It would become a two-dimensional object. This isn't an optical illusion. For the traveler, the distance really is shorter. For the observer, the ship really is compressed. Both viewpoints are equally valid, equally real. They are just different slices of a shared four-dimensional reality we call space-time. Time dilation and length contraction are two sides of the same coin. They are the universe's coordinated defense mechanism, a cosmic pact between space and time to ensure that the one sacred law, the constancy of light speed, is never ever violated. When one stretches, the other must shrink. It's a perfect self-correcting system. This warping of reality solves one problem. For our interstellar traveler, a journey of millennia can be experienced in just a few years. But it introduces a new, more formidable obstacle, a barrier not of time or space, but of substance and energy. As we pour more and more energy into an object to accelerate it, we expect it to get faster and faster. This is how our world works. Push something and it moves. Push it harder and it moves faster. But as we approach the speed of light, something strange begins to happen. Each new push, each new infusion of energy provides less and less of a return in speed. The object begins to resist the acceleration. It behaves as though it's getting heavier. Its inertia, its reluctance to change its state of motion starts to increase. This is the principle of relativistic mass increase. The mass of an object is not a fixed intrinsic property. It is a measure of its energy content. Imagine you are trying to push a colossal boulder up a hill. At the bottom, the slope is gentle. Your efforts move it easily. But as you climb, the slope becomes steeper and steeper. You have to push with monumental effort for every inch of progress. As you near the summit, the incline becomes almost vertical. No matter how hard you strain, the boulder barely budges. The speed of light is that summit. The object you are trying to accelerate is that boulder, and its increasing resistance is its relativistic mass. At 90% of the speed of light, an object's mass has more than doubled. You need twice the energy to achieve the same acceleration you had at the beginning. At 99.9% of light speed, its mass has increased over 20 times. It feels as heavy as a freight train. As you get infinitesimally closer to the ultimate speed limit, the object's resistance to further acceleration balloons toward infinity. You are pushing against a cosmic headwind that has become an impenetrable, immovable wall. The energy you are pumping into the system is not being lost. It has to go somewhere. It is being converted directly into mass. This is the deep, world-changing insight at the heart of relativity. The most famous equation in all of science, E = mc². energy equals mass times the speed of light squared. Mass and energy are not separate things. They are two different faces of the same fundamental entity. Mass is simply a hyper-concentrated, crystallized form of energy, and the kinetic energy of motion as you approach light speed begins to transform back into its material form. You are not just making the object move faster, you are literally making it more massive, and this reveals the final insurmountable barrier. The true reason why traveling at the speed of light is impossible for anything with mass. To accelerate an object that is becoming infinitely massive, you would need to supply it with an infinite amount of energy. To get a single spacecraft, a single grain of dust, a single atom to that final unattainable velocity, you would need to harness all the energy contained within the entire observable universe. And then you would still need more. So Einstein's beautiful, strange new reality, born from two simple postulates, has shown us both a promise and a brutal denial. It shows us how time can be bent to make the cosmic distances subjectively shorter. It shows us how space can be compressed to bring the stars closer, but it also erects an infinite wall of energy, a barrier built from the very interchangeability of existence itself. It has given us the rules for our universe, and the first rule of high-speed travel is that the universe will fight you every step of the way. It will slow your clocks, shrink your ship, and bloat your mass. It will rewrite its own dimensions of space and time to protect its one sacred law. We thought the challenge was building a faster engine, but Einstein revealed the true challenge is far greater. We are not just fighting against the void. We are fighting against the very fabric of reality itself. A reality that is far more clever and far more stubborn than we ever knew. We have chased a ghost through the cosmos. We have wrestled with the strange tides of time dilation. We have witnessed space itself shrink before our imagined vessel. And at every turn, the speed of light has remained ahead of us, a constant shimmering, unattainable horizon. But these challenges, as profound as they are merely the symptoms of a much deeper truth. They are the strange weather patterns on the shores of an impossible sea. Now we must sail into the storm itself. We must confront the absolute final and most elegant barrier the universe has erected against our ultimate ambition. It is not a technological problem. It is not a question of better engines or stronger materials. It is a law woven into the deepest level of reality. A law that says to reach the speed of light you would need to become a god and wield infinite power. A law that begins with a simple deceptive question: what truly is mass? We think of it as substance, as heft, as the stuff of existence. And that is true. But in the language of physics, it is something more fundamental. Mass is inertia. It is an object's profound, stubborn reluctance to change its state of motion. A boulder has more inertia than a pebble. It resists being moved, and once moving, it resists being stopped. To make anything with mass move faster requires a push. It requires an expenditure of energy. For centuries, our understanding was shaped by the genius of Isaac Newton. His laws described a beautifully predictable clockwork universe. If you want to go faster, you simply push harder or push for longer. Apply a constant force and you get a constant acceleration. Your velocity climbs in a steady, reliable, linear fashion. 10%, 20%, 50%, 100%. In a Newtonian world, there is no ultimate speed limit. The universe is an open road, and your only constraint is your fuel tank. This is the world we experience every day. It's the intuitive physics of throwing a ball or driving a car. And for 200 years, we believed it was the whole story. We had no reason to think otherwise. But our intuition, born on a slow-moving planet in a quiet cosmic suburb, had not yet been introduced to the universe's true character. It had not yet encountered the mind of Albert Einstein. He revealed that the universe is far stranger than we imagined. He showed us that mass and energy are not separate things. They are two faces of the same fundamental coin. His famous equation E=mc² is not just about atomic bombs. It is a statement about the very nature of existence. Energy has mass, and mass is a fantastically concentrated form of energy. They are convertible, interchangeable, one and the same. And within that single elegant truth lies the great barrier. It is the reason our cosmic journey comes to a hard stop. Because when you push on an object, when you pump energy into it to increase its speed, you are not just changing its motion, you are also adding energy to the system. And because energy and mass are the same, you are also imperceptibly at first, but with devastating consequences later, making the object more massive. Imagine you are in your starship ready for the ultimate voyage. Your engines ignite a torrent of controlled power, propelling you forward. The initial acceleration is exhilarating. You push past the escape velocity of Earth. You surge past the orbital speeds of the outer planets. You are now moving at 10% the speed of light, 30,000 kilometers every single second. An immense velocity, yet the journey has just begun. At this speed, the universe still seems to play by the old rules. To double your speed to 20% of light, you need a significant but predictable increase in energy. Your ship's mass, its inertia, has increased, but only by a tiny fraction, about half of 1%. It's a negligible change. Your engine barely notices the difference. The universe is not yet pushing back with any real force. You press on. 50% of the speed of light. 150,000 kilometers a second. The energy expenditure has been enormous, but the physics remains familiar. Your ship's mass has now grown by about 15%. It feels heavier. It is more reluctant to accelerate. It takes more fuel to gain each new kilometer per second of speed than it did at the beginning of your journey. You are no longer running on a firm track. It feels as though you are running through shallow water. There is a drag, a resistance that wasn't there before. This is space-time itself beginning to thicken around you. Now we make the next great leap. We will pour unfathomable power into our engines, pushing from 50% of C to 87%. To achieve this next 37% gain in velocity, you might expect a proportional increase in energy. But that is not what happens. To make this jump, you must double your ship's kinetic energy, and you find that your ship's effective mass has now doubled. It is twice as difficult to accelerate as it was when it was sitting on the launch pad. The water you were wading through is now up to your chest. Every step is a monumental effort. You are determined. You have the power of captured stars at your command. You divert everything to the engines. You fight against the growing cosmic friction, this strange inertial drag. Your goal is 99% of the speed of light. Just a stone's throw, it seems, from your destination. The engines roar with a fury that could crack continents. And you get there. 2,96794 kilometers per second. You are slicing through the cosmos at a velocity that defies imagination. But look at the cost. Look at what the universe has extracted from you as payment. At 99% of the speed of light, your ship's mass is not 1% heavier or even twice as heavy. It is now more than 7 times its original rest mass. The universe is fighting your acceleration with immense force. That water you were wading in has become thick, viscous honey. Every millimeter of progress requires a Herculean shove. The relationship between thrust and acceleration is broken. You are pouring ever more energy in for ever diminishing returns. This is where the dream of light speed begins to truly unravel. This is where the numbers become so large they lose all meaning. This is where we enter the tyranny of the nines. You are at 99% of C. Your target is 100%. That last 1% seems so small, so tantalizingly close. Let's try to close just a fraction of that gap. Let's aim for 99.9% of the speed of light. Your ship is already 7 times its normal mass. To add that extra 0.9% to your velocity to creep just a little closer to the light, you must summon a colossal new reserve of energy. The power required for this tiny step is greater than all the energy you used to get from 0 all the way to 99% in the first place. You have to do the entire journey over again in terms of energy just to purchase this next 9 in the decimal place. And should you succeed, your reward is a heavier ship. At 99.9% of C, your vessel is now 22 times more massive. It fights you with the inertia of a small asteroid. The honey has turned to slowly drying concrete. The universe is screaming at you in the language of mathematics to stop, but our ambition is limitless. We have harvested a nebula. We have captured the energy of a supernova. We will not be deterred. Our next goal, 99.99% of light speed. Again, the gap we are trying to cross is minuscule, 0.01%. The energy cost is astronomical. To gain this infinitesimal increase in speed, you must again expend more energy than your entire journey so far. The fuel gauge plummets, the engines glow white hot, the very structure of your ship groans under the strain. And you reach it. Your reward, you are now 71 times your original mass. You are trying to accelerate an object with the inertia of a skyscraper. The concrete is setting fast. Do you see the pattern? The universe is not presenting a barrier you can smash through. It is presenting a curve that stretches into infinity. It is a wall that you can approach but never ever touch. Let's keep going. 99.9999% of the speed of light. To get here, your mass inflates to 224 times its starting value. The next 9 in the series, 99.99999% of C. Your mass swells to over 707 times what it was on Earth. To achieve this, you need the energy output of a small star focused with perfect efficiency into your engines, all for an increase in speed so small it can barely be measured. You are now pushing against a wall of solid granite. One more 9, 99.99999% of C. Your ship now has the inertia of a mountain, 2236 times its rest mass. Another 9, 7,071 times your rest mass. Another 9, 22,360 times your rest mass. With every 9 you add to your velocity, the energy required climbs a near vertical wall, and your ship's mass spirals upwards towards infinity. To add the 12th 9 after the decimal point would require more energy than is contained within the entire sun, and yet you would still be traveling slower than light. You would still see a photon pull away from you effortlessly. You are fighting a battle that is mathematically unwinnable. You are pouring the power of galaxies into your engines, and in return the universe is simply making your ship heavier. It takes all that magnificent energy you are providing, and it does not put it into your velocity. It converts it directly into mass. Your ship becomes a monument to your impossible quest, a man-made object whose inertia approaches that of a planet, a star, a galaxy. Now for the final step, the one that takes you from 99.9 with an infinite number of 9s to exactly 100% of the speed of light. What is the energy cost for that final infinitesimal leap? The equations of relativity provide a clear, unambiguous, and terrifying answer. To accelerate any object with even a whisper of mass to the precise speed of light would require an infinite amount of energy, not the energy of a star, not the energy of a galaxy, not even the energy of all the matter in the entire visible universe. Infinite energy, a quantity that does not exist. It is a physical and logical impossibility. Your ship's mass would also become infinite. It would, in effect, become the entire universe. It would contain all the energy that ever was or will be. This is not science fiction. This is the cold, hard, mathematical reality of the cosmos we inhabit. The speed of light is not a number on a cosmic speedometer. It is a fundamental property of the geometry of space-time. It is the absolute boundary between the world of mass and the world of energy. It is an asymptote, a limit your graph can approach forever, but a line it can never ever cross. You might ask then, how can light itself do it? How can a photon, a particle of light, travel at the speed of light? Because the photon is the ultimate exception that proves the rule. A photon has zero rest mass. It is born at the speed of light. It will die at the speed of light. It never accelerates. It never changes its cosmic velocity. It simply is. The law only applies to things that have mass, things that start out slower than light and try to reach it. For them, for us, for every atom and every starship, the barrier is absolute. So this is the great wall at the end of the universe. It is not made of brick or stone. It is built from the very logic of space-time. It is a declaration etched into every quantum field and every galaxy that there is a fundamental distinction between things that have mass and things that do not. And for us, the children of mass, the speed of light is not a destination. It is a beautiful, untouchable, and eternal horizon. A constant reminder that even for a species that can dream of the stars, the universe still has rules that can never be broken. Imagine for a moment that we have solved the unsolvable. Picture a vessel sleek and silent, humming with a power source that defies our known physics. A machine fed not by fuel but by a fountain of pure energy, limitless and absolute. The first great barrier, the wall of infinite mass, has crumbled. The cosmos, it would seem, is finally open for business. The distant stars are no longer just poetic lights in the darkness, but destinations on a map. So you climb aboard. You strap yourself in the engines, thrum with impossible power, and you begin the final acceleration. 99% of the speed of light. 99.9.999. You are pushing the very edge of reality, the ultimate voyager on the ultimate journey. But the universe is not a simple lock with a single key. It is a grand, intricate mechanism of interlocking laws. And by solving the puzzle of energy, you have not won the game. You have simply unlocked the door to a room filled with even more profound and terrifying impossibilities. The first of these cosmic traps is not hidden in the engine room or in the void outside. It is woven into the very rhythm of your own heart. It is the gentle, relentless ticking of a clock. Einstein's great revelation was that space and time are not separate. They are a single, unified fabric, space-time. And when you move through space at incredible velocity, you inevitably alter your journey through time. It's a phenomenon we have measured. It is not theory, it is fact. Atomic clocks on speeding jets run infinitesimally slower than those on the ground. Astronauts on the space station age a few microseconds less than we do. The effect is minuscule, almost imperceptible in our daily lives. But as your ship closes the final gap to the speed of light, this subtle discrepancy becomes a chasm, a canyon of temporal distortion that swallows worlds. Inside your vessel, everything feels normal. Your heart beats once per second. The ship's clock advances with perfect regularity. You make a log entry, you eat a meal, you gaze at the stars. To you, a day is still a day. An hour is still an hour. But your ship has become a bubble of distorted temporality, a fleeting moment adrift on an ocean of cosmic time. Outside that bubble, reality is screaming forward. For every single minute that passes for you, years might be flashing by on the earth you left behind. For every hour of your calm, quiet journey, a century of human history could be written, lived, and forgotten. Your mission is to reach Alpha Centauri, just over 4 light-years away. At your breathtaking speed, the journey might take you subjectively a matter of weeks, perhaps even days. You will arrive young, vibrant, and ready to explore, but the radio signal you send back, a triumphant message of arrival, will reach a world that barely remembers your departure. The children of your grandchildren might be the ones to receive it, their lives dedicated to monitoring a mission from a bygone era. What if your destination is more ambitious, the center of our own galaxy, 26,000 light-years distant? For you, the passage might feel like a handful of years, a long but manageable voyage. But by the time you arrive, over 50,000 years will have elapsed for the rest of the universe. Humanity, if it still exists, will be a different species, inhabiting a world you would not recognize. The very constellations in the sky will have shifted. The Earth you knew is not just in your past, it is an artifact of ancient history, as remote to your new present as the Stone Age is to us. You have not traveled through space so much as you have traveled through time into a future you were never meant to see. Every kilometer you cross is a bridge burned behind you, not in space but in the shared experience of existence. You become a temporal ghost, a solitary witness to the galaxy's evolution, forever disconnected from your own origin. The journey becomes a profound act of cosmic suicide. You don't die, but your entire world does. Your history, your culture, your loved ones, all of it is consumed by the ravenous passage of millennia that you in your bubble have entirely skipped. The speed of light doesn't just protect the universe from travelers, it protects travelers from the devastating consequences of their own journey. It creates a temporal quarantine, ensuring that a single lifetime remains tethered to a single epoch. It's a law that says you cannot outrun your own time. This isn't a technological problem to be solved. It is a fundamental feature of the way reality is constructed. It is the universe telling us that a journey and its duration are two sides of the same coin, inseparable and absolute. To choose the journey is to accept the price in time, and at the speed of light, that price is everything you have ever known. But let us say you are a particular kind of explorer, a true solitary for whom the past holds no anchor. You accept this temporal exile. You are willing to trade your entire civilization for a glimpse of a distant star. Even then, your journey is far from guaranteed. For space-time has another, even more bizarre trick to play on you. The same mathematics that stretches time also compresses space. It's called length contraction, and it is just as real and just as unforgiving as time dilation. From the perspective of a stationary observer watching you fly past your ship, as it nears the speed of light would appear to shrink. It wouldn't shrink equally in all directions like a deflating ball. It would be squeezed, flattened along its direction of motion. The faster you go, the more pronounced the effect becomes. At 90% of light speed, your ship would look shorter. At 99.9%, it would appear almost like a disk. And in those final, infinitesimal fractions of a percentage closer to light speed, the contraction becomes absolute. Your vessel, a marvel of three-dimensional engineering, would be perceived by the universe as a perfectly flat two-dimensional object, a silhouette moving through the cosmos. And this isn't just an optical illusion, it is a physical reality of your ship's relationship with space-time. Space itself in front of you is being compressed from your point of view. The distance to your destination is shrinking. This is in fact how you are able to cross light years in mere days. You aren't just moving through space, you are fundamentally altering it. But what does this mean for you, the passenger inside? What does it mean for a three-dimensional being to inhabit a reality that has been flattened into a plane? The atoms of your own body would be subject to the same crushing law. The very structure of your cells, your organs, your brain would be distorted beyond recognition to any outside observer. Your existence would be confined to a phantom plane of reality, a sliver of existence hurtling through the void. How could consciousness, a product of a complex three-dimensional network of neurons, even function in such a state? How could life itself persist when its physical dimensions have been so radically compromised? The laws of physics offer no comforting answers. They simply state that this is the consequence. To move at near-light speed is to have your physical form sacrificed on the altar of relativity. Your ship becomes a ghost. You become a spectre, a fleeting, flattened image of a being that once was. This is the universe reminding us once again of the profound unity of its construction. Time, space, energy, and matter are not independent players. They are a tightly choreographed ensemble. If you pull on one thread velocity, the entire tapestry of reality warps around you. Time stretches to infinity. Space contracts to nothing. Mass increases to an impossible weight. You cannot choose which rules you wish to obey. They are a package deal, a complete and total system of cosmic governance. But there is one final consequence, one last devastating barrier that has nothing to do with paradoxes of time or the strange geometry of space. It is a far more primal, more violent, and more immediate threat. It is the simple, brutal reality of impact. We think of space as empty, a perfect, sterile vacuum, but that is a profound misconception. The void between the stars is not truly empty. It is a tenuous soup of particles, stray atoms of hydrogen and helium, microscopic grains of dust, the lonely debris of ancient comets and exploded stars. On average, in interstellar space, there is about one hydrogen atom per cubic centimeter. To our slow, conventional spacecraft, this is utterly insignificant. It is a vacuum more perfect than any we can create on Earth. But for your vessel traveling at a hair's breadth from the speed of light, this sparse dust is not a nuisance. It is a minefield of apocalyptic proportions. The danger lies in a concept you learned in high school physics, kinetic energy, the energy of motion. Classically, it's a simple formula. But in Einstein's universe, as velocity approaches light speed, kinetic energy does not just increase, it skyrockets towards infinity. An object moving at 99.999% of the speed of light carries an almost unimaginable amount of destructive potential. So let's return to your cockpit. You are pushing the limits of existence. Time has slowed to a crawl. Your ship is a flattened phantom, and up ahead, drifting aimlessly, is a single grain of sand, a tiny speck of silicate weighing perhaps a milligram. In a normal encounter, it would do nothing, but this is not a normal encounter. From the perspective of your ship, that grain of sand is not stationary. It is hurtling towards you at nearly the speed of light. When it strikes your hull, the energy released will not be a minor ping. It will be an explosion so vast, so catastrophic, it would dwarf the combined power of all the nuclear weapons on Earth. In an instant, your ship, your impossible engine, your dreams of the stars would be vaporized into a rapidly expanding cloud of superheated plasma. But a grain of sand is a rare encounter. What about those single atoms of hydrogen? Surely they are too small to matter. No, at these velocities there is no such thing as too small. Each individual proton, each solitary hydrogen atom you encounter, becomes a miniature cosmic ray. It will strike your ship's hull with the energy of a high-speed bullet. But this is a bullet that triggers a cascade of deadly reactions. It will shatter the atoms of your shielding, creating a shower of secondary particles, neutrons, muons, gamma rays that will irradiate the interior of your ship, shredding your electronics and your DNA with lethal efficiency. You are not flying through a vacuum. You are flying through a constant, unrelenting hailstorm of high-energy radiation and explosive impacts. Every moment your ship is being sandblasted by the universe itself. No shield we can conceive of could withstand this. How do you deflect a particle that strikes with the force of a bomb? How do you protect a crew from a constant bath of hard radiation generated by the very act of moving? The universe at these speeds becomes actively hostile. The seemingly empty space transforms into a weapon pointed directly at you. The faster you try to go, the more violent the resistance becomes. It's a cosmic checkmate. The very fabric of space punishes you for trying to master it. This is the final, brutal truth. The wall of infinite energy was a theoretical barrier. The paradox of time was a philosophical nightmare. The contraction of space was a geometric horror. But the constant bombardment of interstellar particles is a practical, immediate, and utterly unavoidable executioner. It is the universe's own immune system attacking any object that attempts to violate its most fundamental speed limit. So, what is it that we have truly learned? We have seen that attempting to reach the speed of light requires infinite energy, which is impossible. We have seen that even if you could, you would become a temporal exile, losing your entire universe to the passage of eons. We have seen that your physical form would be crushed into a bizarre, two-dimensional caricature of itself. And we have seen that the journey itself would mean navigating a relentless storm of catastrophic high-energy impacts. These are not four separate problems. They are four different symptoms of the same underlying truth. They are the universe screaming the same message in four different languages. The speed of light is not a goal. It is not a record to be broken. It is not a simple cosmic speed limit like one you find on a highway put in place to be nudged or bent or eventually broken by clever engineering. The speed of light, the constant we call c, is something much more profound. It is the speed of causality itself. It is the pace at which one event can influence another. It is the tempo of the universe's unfolding story. An effect can never ever precede its cause. And c is the ultimate arbiter of that law. To travel faster than light would be to arrive at a destination before you departed. It would be to receive a message before it was sent. It would shatter the logical foundation of reality, the linear progression of past, present, and future. It's like asking what is north of the North Pole. The question itself is a contradiction. The framework it requires for an answer does not exist. The universe we inhabit is governed by this principle. It is a cosmos where cause and effect are sacred. The barriers we have explored tonight, the energy, the time, the space, the impacts, are not cosmic punishments for our ambition. They are the natural, emergent properties of a logical, coherent universe. They are the guardrails that keep the structure of reality intact. Our inability to travel at light speed is not a failure of our imagination or a temporary limit of our technology. It is a fundamental discovery about the nature of everything. It is a sign that we exist within a grand ordered system, a cosmos of sublime and unbreakable rules, and our place is here within it. Not as masters who can bend its laws to our will, but as participants, as observers, as children of the space-time fabric privileged to witness its majesty, forever bound by the very same laws that give it form and beauty. The stars will remain distant, not because we are not clever enough, but because the universe is too profound. We have reached an absolute wall, a law of nature so profound it seems to forbid our most cherished dream of interstellar travel. The speed of light is not a goal to be surpassed. It is a fundamental commandment etched into the architecture of reality. You cannot accelerate a ship with mass to this ultimate velocity. The universe itself forbids it. The attempt requires infinite energy. The journey would take an eternity. But what if we have been asking the wrong question? What if the secret to crossing the cosmos isn't about moving through space, but about commanding space to move for us? For all of human history, travel has meant one thing: propelling a vehicle from one point to another across a static landscape. A ship on the ocean, a car on a road, a rocket through the void. The medium is passive, the vessel is active. But general relativity revealed a truth that shatters this intuition. Space is not a passive, empty stage. It is a dynamic physical entity. It can bend, it can stretch, it can ripple, and if it can do all that, perhaps it can also be commanded. This is where the rulebook of classical motion is set aside, and we enter the strange, exhilarating world of speculative physics. This is where we confront the idea of not breaking the speed limit, but of rendering the speed limit irrelevant. Imagine you are standing on a moving walkway at an airport. You are not running. You might be standing perfectly still, yet the world glides past you at a steady clip. Your local motion is zero, but you are being transported. The ground beneath your feet is doing all the work. In 1994, a physicist named Miguel Alcubierre asked a monumental question. Could we build a moving walkway for the entire universe? Could we create a localized wave in the fabric of space-time itself? A wave that would carry a starship on its crest to a distant star. He did the mathematics, and what he found was both breathtaking and bewildering. The equations of Einstein's relativity did not say no. They provided a blueprint, a recipe for a warp drive. The Alcubierre drive is not a propulsion system in any traditional sense. It does not push against anything. It burns no fuel to generate thrust. Instead, it is a device that would fundamentally reshape reality around a vessel. It would seize the geometry of space-time and contort it into a bubble. Ahead of this bubble, space-time would be powerfully compressed. Imagine grabbing the cosmic fabric and scrunching it up, pulling your distant destination impossibly close. Behind the bubble, space-time would be dramatically expanded, pushing your starting point away at an incredible rate. The starship itself sits inside this warp bubble in a pocket of flat, undisturbed space-time. It is an island of perfect tranquility. The crew would feel no acceleration, no crushing G-forces. They would be utterly at rest, floating in zero gravity. Yet outside their window, the cosmos would be streaming past at a velocity that seems to defy all known laws of physics. 10 times the speed of light, 100, 1,000. Theoretically, there is no upper limit. The ship inside the bubble isn't breaking the cosmic speed limit because relative to its immediate local environment, it isn't moving at all. It is the bubble, this manufactured distortion in reality itself, that is traveling. It is a surfer riding a self-generated tidal wave of space-time. It is an elegant, ingenious, and seemingly perfect workaround. It adheres to the letter of Einstein's law while violating its spirit entirely. It is our one true scientific blueprint for the Starship Enterprise. And it carries a price so steep it may as well be impossible. The blueprint Alcubierre devised requires an ingredient, a material so strange, so contrary to our experience of the universe that we have never directly observed it. To expand space-time behind the ship, you need a field of positive energy. That part is simple. Matter and energy as we know them do this naturally. But to compress space-time in front, to create the leading edge of the wave, the mathematics is unequivocal. It demands negative energy density. It requires a vast quantity of what physicists call exotic matter. This is not antimatter. It is not dark matter. It is something far, far stranger. All the matter you have ever interacted with possesses a positive mass. It has a gravitational pull. It attracts other matter. If you put it on a scale, it has weight. Exotic matter with negative energy density would be the opposite. It would have negative mass. It would exert a kind of anti-gravity, pushing space-time apart. If you were to place a lump of it on a scale, the scale wouldn't register a positive weight. It would register a negative one. The scale would push upwards. If you tried to push it, Newton's laws would seem to run in reverse. It would accelerate towards you, not away from you. This substance violates what physicists call the weak energy condition a fundamental assumption that the energy density of any region of space should always appear positive to any observer. For our entire history, this assumption has held true. It is the foundation of our understanding of gravity and cosmic structure. The Alcubierre drive requires us to shatter that foundation. Does such a thing even exist in our universe? The closest we have ever come to witnessing this effect is in the strange quantum world of the Casimir effect. If you place two uncharged metallic plates incredibly close together in a vacuum, they will be pushed towards each other by an unseen force. This is because the tiny gap between them restricts the kinds of virtual particles that can pop in and out of existence from the quantum foam compared to the space outside them. The result is a region between the plates that has a slightly lower energy density than the vacuum of empty space around it. Technically, this is a region of negative energy density. It is real, it has been measured, but the amount is microscopic, infinitesimal. The Alcubierre drive doesn't need a microscopic amount. The calculations show that to create a stable warp bubble large enough to contain a small starship, you would need an amount of exotic matter with a negative energy equivalent to the mass energy of the planet Jupiter. Imagine an entire gas giant, one of the most massive objects in our solar system, but converted into a substance that has anti-gravity, a substance whose existence is purely theoretical, a substance that may not even be physically possible to create. We are not just talking about an engineering challenge. This is a challenge to the fundamental properties of reality. It's like trying to build a submarine that requires an ocean made of fire. The very material required for its construction defies the environment it must exist in. The solution to faster than light travel requires a form of matter that appears to be forbidden by the universe we seek to explore. But let us engage in a flight of fancy. Let us assume that some future civilization discovers or manufactures this Jupiter mass of negative energy material. Even then, the problems with the warp drive multiply, becoming ever more bizarre and dangerous. The first is a problem of control. The front of the warp bubble is a causal horizon, much like a black hole's. It marks a boundary in space-time beyond which light cannot travel from inside the bubble to the space in front of it. This means the crew inside the ship can send no signal forward. They cannot see where they are going. They cannot send a probe ahead to scan for obstacles. They cannot even send a signal to the front of their own bubble to tell it to slow down or to stop. Once activated, the ship is on a ballistic trajectory, a passenger in a space-time bullet it can no longer command. To stop, they would need to have pre-positioned another supply of exotic matter at their destination, ready to annihilate the bubble upon arrival. It's a ship with an accelerator, but no steering wheel and no brakes. And the arrival itself presents a horrifying prospect. As the bubble travels its leading edge, that region of intensely warped space-time acts like a cosmic snowplow. It gathers up any interstellar particles it encounters along its path, stray hydrogen atoms, photons from distant stars, cosmic rays. These particles become trapped on the front of the bubble, unable to escape, and they are energized to incredible levels. The longer the journey, the more particles are collected, and the more energy they accumulate. Then, when the drive is finally shut down at the destination, this vast accumulation of hyper-energized particles is released in a single explosive omnidirectional burst. The calculations suggest that anyone or anything waiting at the destination would be annihilated by a blast of gamma rays and high-energy particles so powerful it could sterilize an entire planet. The starship would arrive not as a peaceful explorer, but as an unintentional weapon of mass destruction. You could not visit a world without first destroying it. The final paradox is perhaps the most profound. To initiate the warp bubble, you must distribute the exotic matter around the ship, creating that specific geometric shape. But to place the matter outside your ship, you would need to get it there. And since parts of the bubble must travel faster than light, the only way to get the exotic matter into position to start the journey is to have already traveled there faster than light to place it. It is a cosmic catch-22. The warp drive is a key that can only be forged in a fire that lies on the other side of the locked door. It appears to be a brilliant mathematical curiosity, a beautiful, but ultimately tragic dead end. A loophole in the laws of physics, so narrow, so demanding that the universe itself seems to have conspired to make it inaccessible. So if we cannot bend space into a wave to carry us, perhaps there is another way to manipulate the cosmic geometry. What if we could abandon the road altogether? What if, instead of going around an obstacle, we could simply tunnel through it? This is the second great hope for interstellar travel. The concept not of a warp drive, but of a wormhole. Formerly known as an Einstein-Rosen bridge, it is another theoretical possibility that arises directly from the mathematics of general relativity. Imagine once again that our universe is a vast flat sheet of paper. To travel from one point to another, you must crawl along its surface, a journey of thousands of light years. But what if you could fold that sheet of paper? What if you could bring your destination city to touch your starting point? Then you could simply punch a hole through both layers. You would have created a tunnel, a shortcut through a higher dimension, a gateway that connects two vastly distant regions of space-time. You wouldn't be traveling through the intervening space. You would be bypassing it entirely. You would step through a doorway in one part of the galaxy and emerge moments later in another. The light from your destination might take 50,000 years to reach your home, but through the wormhole the journey could take a matter of minutes. You would not have broken the speed of light. You would have simply taken a path where the distance was profoundly shorter. It's the ultimate cosmic shortcut. The idea is deeply seductive, and it has a pedigree. Einstein himself, along with his colleague Nathan Rosen, first explored it. They realized their equations allowed for these topological tunnels connecting one part of the universe to another, or even connecting our universe to a separate parallel one. At first, it seemed as though the cosmos might be riddled with them. But when physicists examined the properties of these bridges more closely, a fatal flaw emerged. They are catastrophically unstable. A naturally occurring wormhole, if it could even form from the violent churning of the early universe, would be a fragile and ephemeral thing. The moment it came into existence, the immense gravitational forces of its own structure would cause it to collapse in on itself. The throat of the wormhole would pinch off into a singularity, a point of infinite density destroying anything that tried to pass through. And this collapse would happen so quickly, so violently, that not even a single photon of light would have time to make the journey. An Einstein-Rosen bridge is not a stable tunnel. It is a cosmic trapdoor that slams shut the instant it opens. So could we prop it open? Could we engineer a stable, traversable wormhole? The mathematics was explored once more, and to the great frustration of physicists everywhere, the same villain appeared yet again. To fight the crushing gravitational collapse of the wormhole's throat, you would need to thread it with a substance that exerts a powerful, outward-pushing gravitational force. A substance with immense negative pressure. You would need that same impossible ingredient, exotic matter. The very same material required for the Alcubierre drive, with its bizarre anti-gravitational properties, is the only thing that could theoretically hold a wormhole open long enough for a person or a ship to pass through it. And again, not just a small amount. You would need a vast quantity of it woven into the very entrance and lining the entire length of the tunnel. We have escaped the energy trap of light-speed acceleration only to find ourselves in a materials science crisis. Both of our most promising methods for cheating the cosmic speed limit depend on a substance we cannot find, cannot create, and which would violate our deepest understanding of how energy works. It seems the universe has placed the same metaphysical lock on two different doors. And even if we could somehow acquire this phantom material, the wormhole presents its own unique set of existential dangers. One of the most profound is the problem of time. According to relativity, space and time are inextricably linked into space-time. When you build a bridge between two distant points in space, you risk inadvertently building a bridge between two different moments in time. Imagine one mouth of the wormhole is kept stationary, while the other is taken on a long journey at near light speed and then returned. Due to time dilation, the clock at the traveling mouth will have ticked slower than the clock at the stationary one. They would now be connected to the same location but at different times. You could step into one end in the year 2050 and emerge from the other end in the year 2040. You would have built a time machine, and with it come all the paradoxes that threaten the logical consistency of the universe. The grandfather paradox, the bootstrap paradox, causality itself, the fundamental principle that cause must precede effect, would be broken. Many physicists believe this is a sign, a clue from the universe itself that such structures are forbidden, that some yet unknown principle of physics, a chronology protection conjecture, must step in to prevent their formation, preserving the rational flow of history. There is also a more immediate physical danger. The throat of a wormhole could be an extraordinarily violent place. Think of the vacuum of space which we imagine as empty. It is not. It is teeming with a sea of virtual particles and background radiation left over from the Big Bang. A particle that falls into one end of the wormhole would travel through it, emerge from the other end, and could then loop back around through normal space to re-enter the first end again. Each time it completes this loop, it gains energy. Its wavelength gets compressed or blue shifted by the intense gravity. Very quickly, an unstoppable feedback loop of radiation would be created, infinitely amplifying itself within the confines of the wormhole's throat. This storm of energy would become so intense, it would likely incinerate anything that tried to pass through and would ultimately have enough power to tear the wormhole itself apart. The very act of being observed, of interacting with the universe, could be what destroys the shortcut. So we stand at a precipice looking out at two breathtaking visions for our future: the warp drive and the wormhole. One, a vessel that commands the ocean of space-time to carry it. The other, a secret passage that bypasses the ocean entirely. Both arise from our most profound understanding of the universe. Both are mathematically sound, and both appear to be fundamentally impossible for the same reason. They require us to perform magic, to summon from the void a form of matter that breaks the known rules of energy. We haven't found a loophole in the law of light speed. We have merely shifted the burden of impossibility. We have traded an infinite demand for energy of a kind we understand for a finite demand for energy of a kind that seems to be a fantasy. It is a grand and humbling realization. The light speed barrier is not simply a practical limitation. It is not a technological hurdle we can one day overcome with a better engine. It appears to be a core structural element of the cosmos. It is the universe's way of maintaining order, of preserving causality. The absolute nature of this cosmic speed limit is not a cage. It is the very foundation that keeps the relationship between yesterday, today, and tomorrow stable and coherent. To travel faster than light through these exotic means is not just to engineer a new form of transport, it is to attempt a full-scale renovation of the laws of reality. And the universe, in its silent mathematical majesty, seems to be telling us that its architecture is not open to negotiation. Our journey through space-time has brought us here to this final shore. We stand before a wall built not of matter but of mathematics, a barrier woven from the very fabric of existence, the ultimate speed limit. The final verdict on our species' most cherished dream is in, and the answer etched into every corner of the cosmos is no. We cannot travel at the speed of light. It is not a technological challenge waiting to be solved. It is not an engineering problem for a future, smarter generation. It is a fundamental truth about the universe we inhabit, a law as profound and as unyielding as gravity itself. Throughout our exploration, we have assembled the evidence. We have followed the clues left by giants of science. And now we must face the three great pillars of this impossibility. The first is a barrier of pure brute force, a mountain of energy that grows to infinity. You are in your starship, pushing the engines harder and harder. You burn through fuel, converting matter into pure thrust. You watch your speedometer climb, ticking off incredible velocities. 90% of light speed, 95, 99. With every decimal point you add, the universe pushes back harder. It's a cosmic headwind of unimaginable force. Why? Because of that elegant, devastatingly simple equation, E equals mc squared. Energy and mass are two faces of the same coin. As you accelerate, your kinetic energy doesn't just vanish. It pours into your ship, into your own body, manifesting as mass. You become heavier, infinitesimally at first, then noticeably. Then, in those final fractions of a percent, catastrophically, your mass swells, bloating towards the infinite. To push an infinitely massive object requires an infinite amount of energy. There is not enough energy in the entire known universe, not in all the quadrillions of stars burning in 100 billion galaxies, not enough to accelerate even a single atom to the true speed of light. The cosmos itself lacks the budget for such a feat. It is the ultimate law of diminishing returns. You expend near infinite power for an infinitesimal gain. The universe demands a price that can never be paid. It's a check that cannot be cashed. The finish line recedes at the very speed you try to approach it. This is the first seal on the door, a seal of pure physics, a declaration that the cost of entry is infinity itself. But even if you could somehow summon this impossible power, even if you could command the energy of a galaxy, the universe has a second, more insidious defense. It would break you by breaking your reality. This is the strange, warping world of relativity. It is not just your mass that changes as you race towards the light. The very dimensions of existence begin to contort around you. Time, that steady, reliable metronome of our lives, begins to falter. For you aboard your ship, the clocks would slow to a crawl. A journey of 1,000 years for those on Earth might be a week, a day, an hour for you, as you nudge ever closer to that ultimate velocity. Your personal time approaches a complete standstill. The moment of your arrival would also be the moment of your departure. The entire journey would happen in a single frozen instant of your time. You would become a statue hurtling through the cosmos, a passenger on a voyage that takes zero time for you. But for the universe you left behind, eons would have passed. Civilizations would rise and fall. Stars would be born and die in the time it took you to blink. You would arrive not as a traveler, but as a ghost from a forgotten past. A relic delivered to a future you could never comprehend. This temporal distortion, this time dilation, is not science fiction. It is a measured, proven reality of our universe. It is space-time's emergency brake, applied directly to your existence. And it is not just time that bends. Space itself rebels. The universe in your direction of travel would compress. The distance to your destination would shrink. Stars and galaxies ahead of you would flatten and distort. Their light would shift, blue shifting into a blinding, searing glare. The cosmos would become a tunnel of ferocious, high-energy radiation. The very space you sought to cross would become your executioner. At the true speed of light, this effect becomes absolute. The universe in your path would contract to a single two-dimensional plane. All distance, all depth would vanish. There would be no journey left to take. You would exist everywhere and nowhere along your path at once. You would not be traveling through the universe anymore. You would have become a bizarre, flattened streak painted across it, an incomprehensible smear of matter and energy. This is the second seal. The universe protects its laws. By warping the very stage on which you perform, it ensures that the act of reaching light speed is synonymous with the act of ceasing to exist in any meaningful way. But these two barriers, the infinite energy and the warped reality, are merely symptoms of a much deeper, more profound truth. They are the consequences of the third and most fundamental reason. The speed of light is not just a speed, it is something more, something elemental. It is woven into the DNA of space-time. We call it K, the cosmic constant, and its true role is not to be a speed limit for matter, but to be the speed of causality itself. It is the pace at which one event can influence another, the speed at which information can propagate through the void. The ripple of gravity from a dying star expands at sea. The flash of light from a supernova travels at sea. The fundamental forces of the universe communicate at sea. It is the universe's own internal processing speed, the rate at which reality can update itself. To travel faster than light would be to outrun consequence. It would mean you could arrive at a destination before you departed. You could see the echo of an event before its sound was made. You could witness a star explode before its light ever left its surface. The orderly procession of cause and effect, the very logic of reality. The chain of events that makes the universe comprehensible would shatter into a million paradoxical pieces. The past would no longer be immutable. The future would be in flux. A universe where C can be broken is a universe without history. A cosmos where logic itself has been torn asunder. So the speed of light isn't a barrier the universe puts in your way. It is the way. It is the structural integrity of the entire cosmic edifice. It is the rhythm to which all of existence must dance. And nothing with mass can ever join the ghostly ballet of light itself. We are creatures of cause and effect, and for that reason, we are locked in a slower, more deliberate waltz. And so we stand here at the foot of this insurmountable wall. Does this mean our destiny is forever bound to this one small planet? Are we prisoners of our own solar system staring out at an unreachable sea of stars? It can feel like a profound cosmic disappointment, a grand dream dashed against the rocks of unfeeling physics. But perhaps we are looking at this all wrong. Perhaps this great limitation is not a prison wall at all. Perhaps it is a clue, the most profound insight we have ever gained into the nature of reality. Imagine you found the blueprints for the universe. You wouldn't be disappointed that they specified the strength of steel or the unbreakable bonds between atoms. You would be in awe of the elegance of the design. The speed of light is just that, a fundamental design specification. It is not a rule designed to frustrate us. It is the principle that makes the universe stable, logical, and beautiful. A cosmos without it would be an incoherent storm of paradoxes, a place where nothing could ever truly evolve or become. The great cosmic speed limit is the bedrock of your own existence. It is the law that allowed the sun to form in an orderly fashion, the law that ensured the earth could coalesce from dust and gas, the law that allows the neurons in your brain to fire in a logical sequence, enabling you to even contemplate the universe at all. We are children of causality, and C is its most sacred guardian. Seeing this limit as a restriction is like a fish seeing the water as a cage. In truth, it is the very medium that gives it life and allows it to explore its world. This universal constant is not a cosmic tyrant. It is the quiet, invisible architect of everything we know. It holds space and time together in a perfect, intricate relationship. It dictates the flow of energy and the structure of matter, and in its unbreachable consistency we find not a cage but a cosmos, a universe of profound and breathtaking order, one where the game has rules, and it is within those rules that the true challenge lies. The most beautiful art is not created on an infinite canvas with no constraints. It is born from the discipline of the frame, the limits of the material. Humanity's future in space will be our masterpiece, painted on the grand but finite canvas of relativity. So if we cannot break the rules, how do we win the game? This is where the human spirit, faced with an absolute barrier, does not surrender but becomes brilliantly, stunningly creative. The impossibility of light speed does not end our interstellar ambitions. It forces them to become grander, more patient, more profound. It forces us to think not on the scale of a single human life, but on the scale of generations of the species itself. If we cannot shorten the journey, we must learn to endure it. And so the dream of the generation ship is born. Imagine a vessel so vast it is not a ship but a world unto itself. A hollowed-out asteroid, perhaps miles in diameter, powered by a fusion sun, its interior lit by a controlled star, with forests, rivers and cities, a complete ecosystem in a bottle, a sealed ark carrying not just a handful of astronauts, but thousands of people, plants and animals, a sliver of Earth's biosphere cast out into the interstellar darkness. The first generation to leave our solar system would never see their destination, nor would their children or their children's children. They would live their entire lives aboard this world ship. Their purpose, their sacred duty, would be to maintain the world, to pass on the knowledge, the culture, and the dream to the next generation. It would be a journey of centuries or even millennia. A slow, patient pilgrimage across the unimaginable gulf between stars. This is not a lesser form of travel. It is an act of supreme faith, a testament to our ability to think beyond our own mortality. It's a solution that embraces the vastness of time rather than fighting it. It transforms the voyage from a frantic sprint into a noble, multi-generational epic. But there are other paths, other dreams born from this same constraint. What if we could cheat time in a different way? Not by accelerating through space, but by stopping our own biological clocks. The dream of suspended animation, of long-term hibernation. The ship would travel at a significant but still sublight fraction of c, but its crew would not experience the passage of time. They would sleep through the long, dark centuries, their metabolic processes slowed to a glacial pace. Monitored by intelligent machines, they would be silent passengers. Their lives paused between the leaving and the arrival. They would board the ship on Earth and awaken years later in a new solar system. For them, the journey would feel as brief as a night's rest. This path requires a mastery not just of physics but of biology. It asks us to solve the deepest mysteries of life and aging, to learn how to switch off the machinery of our own cells. And then centuries later, in a place farther from home than any human has ever been, to switch it all back on again. It's a staggering challenge, a pinnacle of biomedical engineering, but it is not forbidden by the laws of the universe. It is a door left tantalizingly ajar, a way to fit a multi-century journey into a single human lifespan. Both of these visions, the generational arc and the sleeper ship, are born directly from our acceptance of the cosmic speed limit. They are monumental undertakings far beyond our current capabilities, but they are not impossible. They are the kind of grand, audacious projects that a species destined for the stars must learn to embrace. They demand a new kind of explorer, not one who conquers distance with speed, but one who conquers time with patience, endurance, and ingenuity. And what of the other dreams, the whispers from the furthest frontiers of theoretical physics, the ideas that seem to pluck a solution from the realm of magic, warp drives, wormholes? These are the concepts that seem to offer a way around the problem. a loophole in the cosmic contract. But they are not about breaking the speed of light. They are about something far more radical. They are about questioning the very nature of distance itself. A warp drive, in theory, doesn't propel a ship through space at all. It proposes to move space itself around the ship, compressing the space-time fabric in front of the vessel and expanding it behind. The ship would ride this ripple, this warp bubble across the cosmos, and because the ship itself is stationary within its local bubble, it never violates the local speed limit of c. It is the arena that moves, not the gladiator. A wormhole or an Einstein-Rosen bridge is even more exotic, a hypothetical tunnel through the fabric of reality, a shortcut connecting two vastly distant points in space-time. You wouldn't travel across the intervening millions of light years. You would simply step through a door from one place to the other. These ideas are for now pure speculation. They may exist only on blackboards and in complex equations. They might require forms of matter and energy we have never seen, or they may simply be mathematical ghosts, impossible to build in reality. But they are a critical part of our interstellar journey, because they represent humanity's undying refusal to stop asking what if. They are the product of a mind that, when faced with a wall, immediately begins to wonder if it's possible to go over it, under it, or perhaps to simply bend the wall out of the way. These dreams are not a rejection of Einstein's physics. They are a direct conversation with it, pushing his theories to their most extreme and bizarre conclusions, to see what might be hiding in the shadows of our understanding. In the end, our quest to reach the stars is not a simple story of A to B. It is a profound dialogue with the universe itself, and the speed of light is the universe's opening statement. It sets the terms, the rules, the scale of the challenge. It tells us that the cosmos is vast, patient, and subtle, and that to explore it we must become so as well. The barrier of C does not close the door to the galaxy. It simply asks for a higher price of admission, a price paid not in impossible energy, but in ingenuity, in dedication across generations, in a deep and reverent understanding of the laws that govern us. The fact that we cannot travel at light speed is not a tragedy. It is a revelation. It has unveiled the intricate logical structure of space-time. It has shown us the beautiful, unbreakable link between cause and effect, and it has set the stage for our species' greatest adventure. To go to the stars, we must first master ourselves, our biology, our longevity, our ability to cooperate across centuries. We must build worlds before we can even reach for new ones. The universe does not give up its secrets easily, but it lays down its laws with a magnificent, impartial elegance. And in those laws we find not our confinement, but our calling. The great silent star-filled darkness awaits, not as a prize to be won in a simple reckless sprint, but as a destination for a species wise enough, patient enough, and bold enough to undertake the greatest journey of all, within the rules of the grandest game in existence.